Hello again. This is the third video in electromagnetic induction generators. Now, hopefully you should have a pretty good understanding of AC and DC motors, just simple ones with single coils, and so we should understand the role of the commutator, whether you have a split ring or a slip ring. And we're going to talk about generators, and generators are effectively just motors, but where we do mechanical work. So a motor, we have a current carrying wire moving through a magnetic field, or in a magnetic field, and therefore it does work. In a generator, we have a conductor that we move through a magnetic field, so it experiences a changing magnetic field, and it can generate a current. We could also say it generates an EMF or a voltage, depending on if it's connected to a circuit or not, where the current can flow. So we're going to quickly go through generators here. And looking at this diagram, you should be able to look at it and tell me whether or not it's an AC or DC generator. What do you think? 50-50 chance? Have a guess. No guesses in physics. We should identify that these are slip rings, and therefore it's going to be an AC generator. And there's our conductor moving through a magnetic field. We've got to do mechanical work. So that's in this case a crank handle, but it could be a windmill, or it could be one of those wheel things that you find inside guinea pig cages where you make the guinea pig run around. Any sorts of things like that. Anywhere where there's work. Mechanical work is being converted into electrical energy. Okay, and notice that they're saying that the voltage is a sine wave. And it is, and we'll see that shortly. So just recapping, the generators have the AC will have to have slip rings, and the DC has to have a split ring, exactly the same as for motors. And another diagram. Now that looks almost identical to a motor. In fact, you couldn't tell whether it's a motor or a generator because neither of them show whether there's work being done or whether there's current going in. Sort of implying current, but that could be the current that's being generated. So they look exactly the same. And the difference between an AC and this is a DC, this is an AC generator, is of course the split rings. Everything else looks exactly the same because you've just got some conductors in a magnetic field, but it's the split ring or the slip ring that's required. And here's a diagram showing a DC generator, and mechanical work's causing the coil to move this way. There's our conductor, which is experiencing a changing magnetic field. So what would the EMF look like that's coming out of this generator? Something like this, where EMF's here, and there's two curves here. There's an orange one and there's a dashed one. The orange one is the EMF in the loop. And so because the loop is going around and around and around, it's actually generating current that the generated current reverses direction within the loop relative to the loop itself. However, because we've got split rings, that reversal of the EMF means the split rings click in here, and so we're always generating in the same direction. Okay, now these 0 points are when this coil is at perpendicular, and so the only way to get rid of these flat points here would be to have multiple coils, and we saw that when we looked at the motors that came out of drills and things, little hand drills. So simple AC generator, what does it look like? The only difference being the split ring. So in this case we're generating current rather than an EMF. And what would the current look like? Can you have a guess? What does it look like? Just looks like this. So the current actually does what it was doing in the DC one, but because we haven't got split rings, the current actually changes direction. So we have current going in one direction in the external circuit and current going in the other way in the external circuit. And from A to A is one complete rotation. So notice the maximums on both of them, and that would be when the coils are in this position, because the coils are cutting the field lines at the maximum angle, 90 degrees, and therefore we're getting the maximum EMF generated, and therefore we're getting the maximum current. Now in AC again, so here we've got on this scale just degrees of rotation, and these represents each of the points, and so you can see we're going from 10 volts to 10 volts. Maximum being produced when it's in this position and this position and this position. Minimum when it's running, so effectively the coil's moving like that, parallel to the field line, so no current's being generated at that instant. Now there's a link which will take you to some web pages. I'll put that on the OneNote. That will be about electric motors. And in the next video we're going to look at what's called the back EMF and eddy currents. So that was pretty short. See ya.